here the first speaker. The first speaker is Dr. Chul Joo Leec, Seoul, Korea. He has his BSc degree in 1978 and PhD degree in 1990. Visiting professor at the University of Korea, and he also has additional study on Ohio University in USA. Interests: polymerization, and the major topic, organic synthesis. And he also a principal research scientist of Korean Institute of Science and Technology. His paper, I think this paper has been prepared by a lot of researchers, and they nominate Dr. Leec to be the speaker. The paper title is Roles of Molecular Parameters in the Preparation of Syndiotactic Polyvinyl Alcohol Microfibrillar Fiber during Saponification of Polyvinyl ester. Please, you can start, Dr. Thank you.
Yes, thank you so much. Good afternoon, everyone. I'm Chul Joo Leec from Seoul, Korea. Actually, Professor Liu was intended to be here.
Please speak in microphone.
Yeah. Microphone.
Actually, the Professor Liu was intended to be here, but he's not be able to be here. So I will present our recent result instead of him. In this talk, I will present the laws of molecular parameters in the preparation of Syndiotactic polyvinyl alcohol microfibrillar fiber. Polyvinyl alcohol is a linear semi-crystalline polymer which is widely used as fibers for clothing and high-performance fibers such as for the replacement material for natural carcinogenic asbestos fiber and iron rod and ferroconcrete and so on. And for the application of biomedical fiber for such fiber, and for membrane for ultrafiltration, and for films for polarizer, and for films for some packaging, and the embolic materials for killing cancer cells in the human body, and some coatings and some binders and some adhesions. This is the typical aspect of polyvinyl alcohol. The molecular weight is from 24,000 to 440,000, and the number average degree of polymerization is 500 to 10,000. The fibers from this polyvinyl alcohol have high tensile and compressive strengths, and high tensile modulus and high abrasion resistance. However, still there are many attempts to enhance these mechanical properties. To maximize the properties, we should control the molecular weight and the degree of saponification and tacticity. We call it the molecular parameters. It is well known that the stereoregularity of vinyl polymers can change the physical and mechanical properties. Vinyl polymers are classified into three tacticities, such as isotactic, atactic, and syndiotactic ones. This figure shows the syndiotactic stereoregularity, and this chain shows the atactic polyvinyl alcohol, and finally, the isotactic PVA is like this. In the case of PVA, syndiotactic diode, it means syndiotactic two monomeric units, syndiotactic diode, over 55% is usually called as syndiotactic. This slide shows syndiotactic means from the plane of the main chain, one pendant group is upside and the other pendant group is downside, the plane of the chains. While the syndiotactic diode contents of 47% to 54% is called as atactic. This one is totally irregular stereoregularity. And below 45% is called atactic PVA. As you know, syndiotactic PVA has better properties over atactic PVA due to ease of hydrogen bonding between the neighboring chains. From this reason, many attempts are made to increase the syndiotacticity of polyvinyl alcohol. These are the vinyl ester monomers for the preparation of PVA. In order to make the highly syndiotactic polyvinyl alcohol, we should choose the vinyl ester with bulky pendant groups, such as vinyl trifluoroacetate or vinyl pibarate. These two kinds of monomers, they have the very bulky pendant groups. This picture shows the shape of polyvinyl alcohol produced by saponification of vinyl pibarate and vinyl acetate, having different syndiotactic diode contents from 52.8% figure A to 61.5%. As you can see from this picture, PVA with syndiotactic diode of 61.5%, figure J, have very fine microfibrillars. However, PVA with low syndiotactic diode, like figure A and B, is just like a precipitate. Furthermore, we can see the sharp transition between 55% and 56% of syndiotactic diode content, as you can see the picture from E, F, G. E has the syndiotactic diode content is 55.1%, and F is 55.3%, and G is 56.2% of syndiotactic diode. But as you see from these pictures, figure E and figure F don't have any significant evidence of fibrillars. But from figure G, its content is over 56% of the syndiotactic diode. We can see the evidence of fibrillars. The structures of fibrillars having different syndiotactic diode was investigated by X-ray scattering patterns. From small angle X-ray scatterings in the upper figures, we can see the microvoid structure. The evidence is that if a polymer have a microvoid structure, we usually detected evidence, the diamond-shaped patterns of the small angle X-ray scattering. Again, from the small angle X-ray scattering, we can see the microvoid structure. And the syndiotacticity becomes higher, the microvoids becomes regular and elongated. As you see from figure A to figure D. The syndiotic diode content becomes higher from A to D. The pattern becomes very slim, and it means that the microvoid becomes uniform and elongated. It means the PVA chains are better aligned with higher syndioticity. And next, from the wide-angle X-ray scattering, we can know that the crystal orientation was increased with syndioticity. As you see the patterns of these four X-rays. I think many of you is now wondering what is the fibrillars. So this is the photographs of our polyvinyl microfibrillas. The individual fibrillars are the 1 to 50 microns in diameter and 0.5 to 200 millimeter in length. And it has irregular cross-section and needle point-like ends. Its crystallinity is over 48%, and the crystal melting temperature is higher than 260 degrees Celsius. This picture is the polarized micrographs of one individual fibril. This slide shows the molecular weight patterns of PVA. These four pictures have a different molecular weight. The picture of picture A polymer has the highest molecular weight, and the picture D is the lowest molecular weight. The degree of polymerization of figure A is 800, and figure D is 330. And the syndiotic diode contents of all four polymers are over 60%. It's almost the same. As you see from these pictures, higher molecular weight polyvinyl alcohol has microfibrillar structure in figure A, but the low molecular PVA is powder-like shape in the figure D. Before the explanation of this slide, I'm very sorry for the printing quality of these photographs. Maybe my printer is too old. These are the small angle X-ray patterns of same the PVA samples. For figure A of it is the high molecular weight polyvinyl alcohol. We can see the diamond-shaped pattern, but it is not clear. So you may not see the pattern, but the diamond pattern is still there. Is the unique characteristic. Diamond pattern is the unique characteristics of microfibrillar structure. It means the microvoid is in the fibrils. However, the low molecular weight polyvinyl alcohol doesn't have that unique diamond-shaped pattern. Once more, I'm very sorry for the quality of these pictures. These are the wide-angle X-ray scattering patterns of same sample. From these pictures, we can see the degree of orientation. As you can see, higher degree of orientation is in the higher molecular weight PVA fibrils, as you see from these photographs. But for the low molecular weight polyvinyl alcohol, we cannot see any evidence of orientation. Yeah, this slide shows the influence of degree of saponification on the structure of PVA. Low degree of saponification, which is in the figure A and B, have a precipitate-like shape, while the high degree of saponification polymer, like E and F, looks fibrillar structure. From these photographs, we can know that as degree of saponification increased, the fibrillar structure can be developed. From this slide, we can see the low of water during saponification. As you know, the solvent of saponification is methanol, but sometimes we did saponification with addition of some water. Very interestingly, the existence of water is very favorable to obtain the fibrillar structure. Figure A shows the highly oriented pattern of polyvinyl alcohol fibrils, which was obtained under the medium containing water. It means the medium is methanol plus water. And the figure B shows the no orientation, which polymer was obtained by a water-free medium, only water-free methanol. This slide, from this slide, we can see the morphologies of polyvinyl alcohol fibrils having different degree of saponification. As you see, as this degree of saponification becomes higher, the fibrils becomes longer and narrower. The figure A has a low degree of saponification. Furthermore, the tensile strength of higher degree of saponification, the fibrils in the figure B, is 12 gram per denier tensile strength, but the tensile strength of figure A is quite low. Therefore, we try the X-ray evaluation, and the results are in the next slide. As you see by these pictures, the polyvinyl alcohol with a higher degree of saponification has strong diamond-shaped pattern. The picture B. It means the microstructure is very regular and elongated microvoids. From the wide-angle X-ray patterns on the right side, we can see the higher crystal orientation of a higher degree of saponification. Therefore, we can know that the high tensile strength of a PVA fibril with high degree of saponification is mainly due to the orientation of the chains. This figure shows the effect of Syndiotacticity on crystallinity. The crystallinity was increased in accordance with the increase of Syndiotactic diode content. As you see, symbiotic diet content is right over here. So as the symbiotic diet content is increased, the crystal unity is increased. And this and the pictures on the left side. This picture is the wide-angle X-ray diffraction of PVA fibrils with syndiotic diet content of 63.1% and 58.4%. Low syndiotic diet content, it means that the figure B figure shows a small over around 20 degrees. It's a small, it's a small overlap in contrast over figure A. It's a higher syndiotic diet. Higher syndiotic diet PVA in figure A, the peaks are very narrow and sharper. It means larger crystals are formed in higher syndiotic PVA. The scheme is postulated the PVA chains. The left side is atactic and the right side is syndiotic. As you see from this picture, for syndiotic polyvinyl alcohol, the chance of hydrogen bonding is more higher than atactic polyvinyl alcohol. This is our conclusions. First, we have demonstrated that control of molecular parameters such as syndiotacticity, molecular weight, and the degree of saponification for the microfibrillation of polyvinyl alcohol is very important. Second, to find critical syndiotactic diet content of polyvinyl alcohol for vinyl pivalate and vinyl acetate were co-polymerized. The structure of polyvinyl acetates with a similar degree of polymerization of 7,800 prepared by saponification of polyvinyl pivalate and polyvinyl acetate, showing a consistent sharp transition between 55 and 56% syndiotic contents. Polyvinyl alcohols with low syndiotic diet contents have shapeless morphologies, but at 56% of syndiotic diet content of the polymer were fibrous with a higher degree of crystallinity and orientation of the crystallites. This is the final slide. The polyvinyl alcohol with degree of polymerization over 800 and syndiotic diet content over 62.5% revealed a well-defined fibrous morphology. Each fiber is composed of a number of microfibrils. As the degree of polymerization of PVA decreased, structural changes as well as morphological changes were observed. Therefore, the microfibrillar polyvinyl alcohol fibers with syndioticity of 62% were essentially obtained when the degree of polymerization is higher than 800. Thank you for listening.
Thank you, Dr. Lee, for your interesting presentation.